at operations with radical expressions. So a radical expression is basically going to be any expression, meaning that it can have numbers or variables in it that also involves radicals. So we're going to be looking at how to multiply, divide, and also add and subtract these. Now, two properties that we're going to need to be able to use. So the first is our multiplication property of radicals. And we've really already used this property, we just didn't call it this. So what it tells us is that if I have the nth root of two things that are being multiplied together, we're allowed to break that apart into two separate radicals. And we do this because it allows us to be able to reduce. Likewise, we also want to be able to do something similar when we have two things that are being divided together. So if they're under the same radical, that means that we can reduce them to be two separate radicals with the same index. And that's important. Notice that my index is n on the left side, and when I switch them to two separate radicals, either with multiplication or division, my index is still n for both of them. So let's look at maybe how we might use these. So notice that on our first one, we have the square root of 32x to the 8th. So we want to look at both of the components of these. The first is going to be the number, and then the second part is going to be the variable. So we want to look at, can we break this apart? Remember that our goal is to always have exponents for whatever index it is that we have. So in this case, our index is 2 because we don't have one. So what we want to look at is, 32. So if I were to do a factor tree for 32, notice that 32 is not a perfect square. I can't take, 2 squared is 4, 4 squared is 16. Notice that there's not anything that multiplied by itself gives us 32. However, we can reduce this, and we've done some of this in the past, hopefully, in some of our other algebra classes, but let's just review this. So notice that if I were to break this apart, it would be 2 times 16. And then 16 is going to be 4 times 4. So once I break it down into something that is a perfect square, I can go ahead and stop there. Obviously, these aren't the prime factors because we would need to break our 4s down further and further. But basically what we're looking for is when I can have two numbers, or basically a pair of numbers, that are the same. And the reason that I'm looking for pairs here is because my index is 2. If my index was something else, like say 3, I would need to be looking for groups of 3 because remember that my goal is to rewrite this using multiplication. And we want to use our exponents that are going to reduce with our radical. And since in this case our radical is a square root, we want to use exponents of 2. And then similar to what we did in our last lesson, remember that I have an exponent property that tells us that we can rewrite exponents as raising a power to another power. So if I'm looking at 8, I want to say, okay, what times what gives me 8? And I want to use 2 because that's the exponent that I'm trying to get. Well, that would be 4 times 2. So I'm going to put my 4 on the inside and my 2 on the outside. Now the only difference between here and what we did before is notice that this time I have something that's not going to reduce. My 2 doesn't have an exponent of 2, which means that I can't group it with my other 2 things. So the way that we kind of get around that is notice that we could write our 4x to the 4th to the 2nd power, because both of them have a squared on the outside. And then we're going to go ahead and, like our property tells us, write out a separate radical and break them apart. And the reason we do this is because notice that my first radical, my radical and my exponent will reduce, so we're just left with 4x to the 4th. And since our square root of 2 can't reduce, it's just going to stay the same. So I end up with the square root of 2. Now remember, whenever we're dealing with even roots, we always want to check if we need absolute values. And in this case, technically it would be okay to put absolute values around our variable x to the 4th, but also remember that x to the 4th is an even power. So even if we plugged in a negative there, we would still end up with a positive. So it would be okay to just leave it as 4x to the 4th times the square root of 2, but it wouldn't be wrong to go ahead and add the absolute values around our x to the 4th. So let's look at our next one. We have 16a to the 24th times b to the 13th, and those are all under a 4th root. That is a 4 as my index. So let's think about, okay, well, we don't know. If you don't know your fourths, that's okay. 2 times 2 times 2 times 2 does indeed give us 16, which is helpful, because then we can just say, okay, this is 2 to the 4th, and that takes care of that. And then for my a to the 24th, again, I'm trying to find 2 different numbers that can multiply together to give me 24, and I need one of them to be 4. Because then we can use our exponent property and say a to the 6th to the 4th would give me a to the 24th. However, hopefully we've noticed, okay, well, b to the 13th, there's no way for us to write that as 2 numbers multiplied together, one of them being 4, and end up with 13. 13 is a prime number. That's not going to work. So what we end up having to do is to kind of work our way around that. We still need to simplify it as much as possible, just like we did with our 32 on the other side. We were able to break it apart with multiplication and break off a 16. So here, we want to do a similar process. Okay, well, 4 doesn't go into the 13, but is there a number, or in this case, an exponent that we could break off that 4 will go into? Well, notice that we could break off a b to the 12th, and that's going to be helpful because 4 does go into 12. Well, notice that if we do break it off, that does mean that we're going to have something left over, which in this case is going to be just 1b, and that's okay. So now notice that we can rewrite our b to the 12th as b to the 3rd to the 4th, again with our b left over. And we do this because now we can say 2a to the 6th, b to the 3rd, all raised to the 4th power, times, again, using our multiplication property, I have the 4th root of b. And we do that because on our first one, our 4th root and our 4th power will reduce, and we're just left with 2a to the 6th, b to the 3rd, times the 4th root of b. And in this case, notice that my b to the 3rd could be negative, so I'm going to put absolute values around it. And that would be my final answer. division, it's going to be a little bit different because we need to talk about rationalizing. So we've used rationalizing in the past whenever we had things, say, like 1 over the square root of 2. We don't like square roots, or basically irrational numbers, to be in our denominators. So what we do is we rationalize them, meaning that we make them a rational number. And hopefully we recall, when I have something like a square root of 2, I multiply by the square root of 2 to the top and the bottom, and I get the square root of 2 over 2. And that's okay whenever I just have a square root. But notice that the reason that works is because we kind of skipped a step here. We didn't actually write it out. So notice here in between, it would actually be, well, 1 times the square root of 2 is the square root of 2. And then the square root of 2 times the square root of 2 is the square root of 2 squared, because I have 2 of them. So the reason that it ends up just giving me a 2 in the denominator is because I have 2 of those. So I get an exponent of 2, and our exponent is the inverse of our radical. But let's say we had something like 1 over the third root of 2. Well, now, if we did a similar process to like what we did before, I would multiply the top and the bottom by the third root of 2. But if we do that, notice I have a third root of 2 on top, which isn't bad. But then notice that we have the third root of 2 squared. And that doesn't reduce with our third root, so it doesn't really help us rationalize. Well, notice that in order for my radical to reduce with my exponent would need to be 3. So basically, we kind of have to think about, okay, if I have a third root and I only have a 2 there, what would I need to multiply by in order to get it to a 3? So we can kind of look at our inside exponent. Now, on our first example, I wrote my 2 on the outside, but it would have been just as fine, and it means the exact same thing if I had written it on the inside. Those two things are equivalent. So notice here that if I start with a 1, so I have a 2 to the first, and I need to get it to a 3 this time instead of a 2, notice that if we multiply by 2 squared, now we have 2 to the third, which is what we need because my third root now reduces with my third exponent, and we just end up with 2. But remember that whatever we do to the bottom, we must also do to the top. So we would need to multiply by a 2 squared to the top, which would be the third root of 4. So notice in general, what I'm doing is I'm saying, what am I missing to get to my index? Because remember, your index is the number that we need to get to, because then that's what's going to allow us to reduce. So in general, if I have something that looks like 1 divided by the nth root of b to the x power, we need to multiply by to the top and the bottom. So notice, like in the example with my third, okay, my index stays the same. It's still going to be n. And notice that I also didn't change that base of 2. It's still going to be the same base. Now notice what is different though is my exponent. I'm not just going to multiply by b to the x or whatever I have there. What we ended up doing was taking our index, which is 3, and we subtracted the exponent that we already had, which was 1, and that gave us 2. So in this case, I have an index of n, and I need to subtract off the exponent that I already have, which is x. And then basically that will give me whatever I need to get me to the correct number. But remember that what we do to the bottom, we must also do to the top. And this rule will work no matter what type of index we have. So let's look at some examples. So notice that on our first thing is we have a square root of a division problem here. So remember, using that property that we had before, I'm going to break this apart into two separate radicals. And in this case, we have square roots. Now on top, hopefully we notice that we could rewrite this as x to the third squared. So my square root and my squared would reduce. And again, notice that my y to the 7th, well, 2 doesn't go into 7, so I can't just write them using my exponent property. I'm going to have to break something off like we did before. Well, notice that the closest thing that we're going to be able to break off is going to be y to the 6th. And then we would have a y left over. And when we do that, notice that we can now rewrite our y to the 6th as y to the third squared, just like we did our x. And then we can have our leftover square root of y. So simplifying, on the top I'm going to have an x to the third, and on the bottom I'm going to have a y to the third. But notice that we also have a square root of y. So I've simplified out all of our square roots that we can simplify things out of. I cannot simplify the square root of y any farther. However, we don't want to leave that square root in our denominator. Right now, we have an irrational number in our denominator. So we do need to multiply by something. And in this case, we're going to multiply by, well, notice that my index here is 2. So my index will still be 2 for whatever I'm multiplying by. My x, or basically the exponent that I already have for my y, is an understood 1. So if I did n minus x, which in this case would be 2 minus 1, I just end up with 1. And that's why in the past you've always just seen, oh, multiply it by itself, because we have a square root. So when we do 2 minus 1, we just end up with 1. So we just end up with what we already had there. And again, the reason that we do that is because now, when I multiply, I still have an x to the third on top, and I'm going to have a square root of y, but now that it's in my numerator, that's okay. And remember, the whole reason we do this is because I have a square root of y times the square root of y, which gives us the square root of y squared, which are going to reduce with one another, so I just have a y. And then we just need to combine our denominator one step further, and so we get y to the fourth. Then the only thing we need to be careful about is, because these are square roots, remember that we need to worry about negatives. So notice that my x to the third could potentially be negative, so we need to make sure that we add those absolute values. So next up we have a fourth root of 6 divided by 5x. So again, I'm going to break this apart. So we would have the fourth root of 6 divided by the fourth root of 5x. And this time notice that there's not a way for me to break anything apart or simplify anything, because I can't write things with exponents of 4. So that's as simplified as my radicals get. However, notice that we have radicals in our denominator, so we need to rationalize. And this time when we rationalize, we're going to have to use our little property and decide, okay, my n is 4. Now, our x on both our 5 and our x, we're just going to go ahead and rewrite this as one expression. So notice that our x is 1. So n minus x is going to give us 3. So that means that we need to take what we have and we're going to multiply that now by the 4th root of 5x to the 3rd power. Because now when we do that, well, 5x times 5x to the 3rd gives us 5x to the 4th, which is what we want because now my exponent is the same as my index. So those will reduce, and then notice on top we would have the 4th root of 6 times 5x to the 3rd. So notice on bottom, since they will reduce, I'll just be left with a 5x. And then we just want to multiply everything out. So if I did 5 to the 3rd, we get 125. And then if we multiply that by 6, we get 750. And then x to the 4th, sorry, that should be, x to the 3rd is just going to be x to the 3rd. And then again, notice that I do have an x that has come out of my radical. So I'm going to go ahead and put absolute values around it because we have a 4th root. So in general, we have a couple of guidelines when we're trying to simplify radical expressions. We want to make sure that our index is as small as possible, which a lot of times we can't do anything about, but sometimes maybe we can reduce some things so we can. We want to make sure that our radicand, remember that's the stuff on the inside, contains no factors other than 1, obviously, that are nth powers. Meaning that if I have a square root, kind of like when we had the 32, I could break apart a 16. So we want to make sure that whatever's in there, we can't break anything off of that we could reduce. So like if we have a 7, well obviously 7 is prime, so no matter what our index is, we're not going to be able to reduce that 7. The radicand can contain no fractions, and we can have no radicals appear in a denominator. And then the other thing that we're going to need to use whenever we start trying to simplify are what we call like radical expressions. And these are radicals with the same index and radicand. Or remember the things that are in the inside of our exponent. So some examples. If I had, say, the square root of 4x and 3 times the square root of 4x, well, notice that my both of them are square roots, and I have a 4x underneath my radical on both of them. So those would be like radical expressions. Now notice if I had something like the 4th root of, say, 2x squared and the 5th root of 2x squared. Well, my radicand is the same, but now, my index is not the same. So these would not be like radical expressions. And then the last thing that we could see would be like if I had the 3rd root of 2x and the 3rd root of, say, 2x to the 3rd. Well, notice that now they have the same index but different radicands, so those would not be like radical expressions. So let's go ahead and try and simplify. So here we're multiplying. So usually what I go ahead and do is I just say let's take care of our numbers on the outside first. So I'm going to do 5 times 3 is going to give us 15. And then we need to try and reduce our things on the inside. And usually it's helpful to go ahead and multiply it out. So I have a negative 12 times an 18 is going to give me a negative 216. Then I have an a times an a squared, which gives me a to the third. And then I have a b to the fourth times b squared, which is going to give me b to the sixth. So hopefully we notice that we can pretty easily rewrite. So our a to the third is already to the third. And then our b to the sixth, we can write as b squared to the third. What's going to cause issues is our 216. So I would go ahead and make a factor tree. So notice that 2 factors of 216 might be like 12 and 18. Well, 12 I can rewrite as 4 times 3. And 4 we can rewrite as 2 times 2. Then our 18 we could rewrite as, say, 2 times 9. And then 9 is going to be 3 times 3. Now remember that whenever we're looking for groups, this time I'm looking for groups of 3. And the reason for that is because my index is 3. So notice that we have 1, 2, 3 2s. And we also have a 1, 2, 3 3s. And that's helpful because now we can rewrite this as, we need to put a negative in front of one of them because our 216 is negative. But we can say that this is negative 2 to the third times 3 to the third. And we could go ahead and pull it all out for our exponent. But also remember that because they all have 3's this time, I would end up with 15 times a negative 2 times 3. My cubed on my a is going to reduce, so I just have an a, and then I have a b squared. So then our last step would just be, okay, negative 2 times 3 gives us negative 6, and then negative 6 times 15 is going to give us negative 90. So I have negative 90 ab squared. Now the important thing is to remember is that we do not want to add absolute values this time, because this time we have an odd index, not an even index. And so that would be my final answer. Now next up we have the square root of 98 minus 2 times the square root of 32. And a key thing that we need to know is we can only add or subtract like radical expressions. So we talked about a couple pages ago what a like radical expression is. And in order for us to be able to add or subtract things, they have to be like radical expressions. Well, notice that right now I have square roots, which is good because that means that my indexes are the same. However, notice that our radicands are not the same. I have a 98 and a 32. So what we need to try and do is reduce those as much as possible. So again, I'm going to go back to my trusty factor tree. So 2 goes into 98 49 times, and then 49 is a perfect square that has 7 and 7. Then I look at 32. Well, 2 goes into that, 16 times, and 16 is going to be a perfect square of 4 and 4, which means that we could rewrite this as 2 times 7 squared minus 2 times the square root of 2 times 4 squared. So notice that for my 7 and my 4, because they have a squared along with them, they would reduce with my radical. But then I have a square root of 4 that stays, a square root of 2 that stays inside both of them. Well, then we can just multiply together. So 2 times 4 gives us 8. So then we have 7 minus 8. And because my square roots of 2 are now both the same, it can act just like a normal variable. If I had 7x minus 8x, we would end up with negative 1x. But instead of an x here, I have a square root of 2. So we're able to subtract those two things. And that would be our final answer. So notice here, we have a binomial times a binomial. So we are just going to have to multiply it out like we've multiplied out other things in the past. So I want to do my 4 square roots of 3 times 3 square roots of 2 first. And we end up with 4 times 3 gives us 12. And then the square root of 3 times the square root of 2 gives us the square root of 6. Then we would do 4 square roots of 3 times negative 6, which is going to give us negative 24 square roots of 3. Then we would have 5 square roots of 2 times 3 square roots of 2, which is going to give us positive 15. And then I have a square root of 2 times the square root of 2, so that's just going to be 2. And then lastly, I have 5 square roots of 2 times negative 6. So I end up with negative 30 square roots of 2. So then I just need to simplify. I have 12 times the square root of 6 minus 24 square roots of 3 plus 30 minus 30 square roots of 2. And we could go ahead and leave our answer like that, but in general, usually we write our radicals in descending order, and then any constants that we have, we're going to write at the end. And so that would be our final answer. Now the last type of problem that we have to look at. So we have a word problem here, which is fine. It's just an application problem. So it says, golden rectangles have been used by artists and architects to create beautiful designs. Many golden rectangles appear in the Parthenon in Athens, Greece. The ratio of the lengths of the sides of a golden rectangle is 2 divided by the square root of 5 minus 1. Now, the golden rectangles appear a lot, and that's because not only are they very architecturally sound, meaning that they can withstand a lot of weight and help to give the structure like a good base, which is why they got used a lot in architecture. And notice that in the case of the Parthenon, it's withstood, thousands of years. It's also true that they're very appeasing for the human eye to look at. So actually a lot of postcards will use a golden ratio for the measurements of the sides of a postcard. And the reason is because it's thought that our eyes are drawn to the ratios of that postcard then. So in general, though, that ratio is specifically 2 divided by the square root of 5 minus 1. which isn't a super pretty number to look at, but it's not awful. And notice that our directions say to refer to the beginning of the lesson, which is just that little excerpt up above. But then we want to use a conjugate, and we haven't really heard of a word conjugate before, to rationalize the denominator. And the reason it says to use the conjugate is because notice that if I just multiplied by the square root of 5, well, then my square roots of 5 would reduce, but then I would also have to multiply it to the negative 1, so we would still have a square root in our denominator. So if I had something like the square root of x plus b, my conjugate would be the square root of x minus b, or vice versa. If I have something in the subtraction, then I just flip that middle symbol to be the opposite. So in this case, we need to multiply the top and the bottom by the square root of 5 plus 1 in order to reduce. And we'll look at why we choose that in just a second. So we're going to go ahead and multiply it out. So I have 2 times the square root of 5 plus 1 on top. And then on bottom, we have a binomial times a binomial again. So I'm just going to multiply it out or FOIL it out like we have in the past. So square root of 5 times square root of 5 just gives us 5. The square root of 5 times a positive 1 gives us a positive square root of 5. Then a negative 1 times a square root of 5 gives us a negative square root of 5. And then we have a negative 1 times 1. Well, hopefully we've noticed that that middle 2 end up reducing with one another, which is why we chose the opposite sign, because that's what allows those two middle terms to reduce. So we end up with 2 times the square root of 5 plus 1. And now notice in our denominator we have 5 minus 1, which is 4. So then our last step is going to be, well, notice that 2 goes into 4 2 times. So we can reduce that. So we end up with the square root of 5 plus 1, all divided by 2. And that would be our final answer. Now these ones aren't as common as the ones where we just have a single square root or root in our denominator, but they do come up from time to time. So we do need to remember that if I have addition or subtraction outside of our radical, but it's still in that denominator, we have to multiply by the conjugate instead.